everybody. Thank you for the introduction. I'm Eike. I hear echo. I'm going to talk about TinyGo, which is a new Go compiler for embedded systems and WebAssembly. I started the project because the main Go compiler wasn't able to do this in a good way. But I'll show a demo first. So let's see. This is the. You may recognize this. This is a small Blinky example, like you would use on an Arduino, for example. Even if you don't know Go, you probably recognize how it works. It configures an LED, and then in a loop, it turns it on and off. And I can flash it to a microcontroller using this command. It's compiling and flashing. And probably not visible from behind, but this is the LED blinking, and this is written using Go. So I think that's pretty cool. However, so this is what Arduino does as well, basically. But I think we can go even further by simulating this board. This is the same program running inside the IDE. And you can see the same LED blinking here. And this is especially useful for small modifications to see what happens. For example, you might want to blink a little bit faster. This just works. I won't go into detail how this exactly works. But basically, it compiles the same program to WebAssembly instead of to a native binary. But it uses the same hardware abstraction layer. So the backend, so to say, of the hardware abstraction layer talks to the JavaScript in the simulator. But it's the same layer. So the machine package here just talks to WebAssembly instead to the JavaScript instead of to the real hardware. And I think this can be very productive, a productive way to write software. So for example, here I have a slightly more complicated example. And I wrote this entirely in the simulator, and it's visible here. Just adjusting the brightness and the color speed, etc., all in the simulator. And when I ran it so this is on the simulator, and this is how I run it on the board itself. It's compiling. And here you see the same program running in, sorry? Oh, there you go. I think this is visible because the LEDs are pretty bright, but this is basically the same program. And I discovered a bug in the simulator, but otherwise it worked on the first try. So I think that's pretty cool. Let's see, that's a demo. So if you don't know Go, it's a programming language designed by Google about 12 years ago. which is actually pretty young for a programming language. Python is 30 years old, and C is probably older than most of you. So it's pretty young. And Google designed it to solve their problems. So it was intended for large servers with many cores. So it was entirely not designed to do this. But I like the language. It's quite simple to learn. And I started getting into embedded development myself via Arduino, like most people probably. And I really liked being able to control hardware because electronics was a hobby of mine before, but I sort of ignored it because I didn't get any further. But at some point I discovered I could program these electronics using software, and I got very excited. But I really didn't really like the C++ dialect that Arduino uses. It's fine, but not what I like. So when I discovered MicroPython, which is used on the MCH batch, for example, which is written in Python, I basically fell in love. I contributed some patches, and I really liked the project. Unfortunately, I also wanted to do LED animations like this, and it's just a little bit too slow for what I wanted to do. So at that point, I also discovered Go, as I previously described. And I was like, I mean, how hard can it be? So I just hacked around and see how far I got. And 4 years later, it's gotten quite far. Most of the Go programming language features already work, like basically all basic features. And so what mainly doesn't work is, for example, parallelism. So you can't use multiple threads or multiple cores, because like most of these chips don't even have multiple cores. And the reflect package, which is runtime reflection, like runtime type information, etc., which partially works, but it's not complete enough for JSON serialization, for example. But that's something I work on. But because there are small parts that are still missing, large parts of the standard library don't compile, because one dependency of a dependency somewhere doesn't work yet. But otherwise, most of it just works. It's the same language. So my goal is to be compatible with the wider Go ecosystem. And of course, CGO, which is a way of Go to interact with C code. The main Go compiler has trouble cross-compiling when CGO is in use. However, in TinyGo, the main way to use it is by cross-compiling, because the chip here is different than my x86 laptop. So, in my opinion, in many cases, it works even better than the normal implementation. Let's see. Yeah, so I want to just say quickly, I use the word embedded software and microcontrollers somewhat interchangeable, but it's not quite the same. Embedded systems are, it's a bit of a vague category, but basically the way I describe them is everything that runs code but doesn't look like a computer, which is almost every electronic device nowadays. A more specific category is microcontrollers, and this is just some general properties that most of them have, but there are always exceptions, of course. There are many architectures, there's a wide range of RAM, but it's usually very limited. They are relatively slow. They execute code directly from flash memory instead of loading it into RAM first, like Windows or Linux do, for example. They don't have memory protection usually, and they don't have virtual memory. However, what they do have is a large range of peripherals, which means they have various ways of interacting with other non-programmable chips, for example, gyroscopes or displays or whatever. Programming these chips is almost always done in C or C++. There are some exceptions, like the batch, for example, but underneath is also C and C++. Sometimes other languages are used, like Rust or maybe even Ada in some cases, but almost always it's C or C++. But how this is done is usually by using silicon vendor-provided hardware abstraction layers, which tend to be rather difficult to use. Well, not difficult, but not very portable, because you're locked into the system. And, well, it's software written by hardware designers, which is not usually of the greatest quality. So, yeah, that's one reason why I don't really like using C. But there are also other practical reasons. For example, C is by default very memory unsafe. According to both research by Microsoft and Google, 70% of their security vulnerabilities were in memory due to memory unsafety. For example, double freeze or buffer overruns or things like that. And so that's one reason to not use a language that has this unsafety. Rust, for example, solved this in a very interesting way. Another reason is undefined behavior. Technically, memory unsafety is, I guess, also undefined behavior. But there are also integer overflows, for example, and many other things that seem to work, but sometimes they don't. And C is often presented as portable, but actually it isn't really. It's sort of, but all the implementations are slightly different. Integer sizes can differ. Available headers can differ. Yeah, it's a little bit of a mess, but because of the long history of C. So that's why I prefer using other languages. One contender is, of course, Rust, and I think it's a very good language for programming microcontrollers, especially for safety-critical systems. But there are some reasons why you might not want to use it. For example, so it has gotten a lot better over the years, but it's still a little bit hard to learn. And but for example, you might also have existing Go code you might want to use on a microcontroller, or existing developers that are familiar with Go but not with Rust. So having options is great. But then again, Rust is probably a nice language, it's just not my language. Let's see. So that's why I like using a different language. And now I would like to go into a little bit more detail how a TinyGo is structured, because most people probably think of compilers as a big black box, and you put source code in, and an object file comes out in the end. And so it is very complicated when you look at it this way. But like all complicated problems in software engineering, you just split it up into multiple smaller parts that are more easily solvable. So for TinyGo, for example, I used Go has some standard library packages which already support parsing and type checking the language, which is useful. And so what TinyGo basically does is convert this this intermediate form that these okay, let's back up a bit. Basically, compilers are structured in layers, and every layer simplifies the code a bit and optimizes them in a way that is appropriate for this layer. And in TinyGo, I use a few for the first part, I use the standard library packages, as I described. And for generating object files, I use LLVM, which is a compiler framework. Many well-known compilers are written using LLVM. For example, Rust, as I mentioned before, Swift, Clang, and many other compilers are using LLVM in the backend. What it does is basically a compiler can generate a language-independent intermediate representation, and LLVM will then optimize this language-independent form and generate machine code in the end. So that takes away lots of the hard work of writing a compiler. So basically what TinyGo does is only to convert this Go intermediate form into LLVM intermediate form, which for the most part is pretty simple, but of course in Go you can start coroutines, which are kind of graying threads. But of course LLVM doesn't support things like that, so that's basically a runtime call. So this part of the compiler is not too difficult. What is more interesting probably is the runtime. The runtime basically does a lot of stuff behind the back. You can see a list here. When a chip like this resets, nothing is initialized yet. Memory has to be initialized, clocks have to be initialized. Often the chip has to be set to a higher frequency, stuff like that. So that's the startup code, which is in the runtime. And then it calls the main function, as I showed earlier in the code, like this one. And of course, there are many other things like scheduling. Go has Go routines, which are, as I said, basically green threads. And the scheduler is there to start them and switch between them and prioritize them, etc. And Go has channels, which are, I think other languages have them, but not frequently used, I think. Erlang, yeah, probably. Thank you. I think you're correct. So that's one thing that's implemented in the runtime. And garbage collection, of course. The Go language specification doesn't describe how memory is managed. It just says this allocates memory. In practice, that means you have to use a garbage collector. like Java or JavaScript or I believe Erlang, but I'm not sure. And I basically copied the garbage collector from MicroPython, more or less, at least the design. And it's just a few hundred lines, I believe. It's like a textbook implementation of a garbage collector. But that's also in the runtime and time handling, because every chip has a different way of controlling time. Many have an RTC, a real-time clock, real-time, because at the chip reset it's set back to 0. But this specific hardware implementation has to be converted back to the time.now and time.sleep in Go. And that's what the runtime does. And of course, other things like the hash map implementation, which is of course optimized for size instead of for speed, and many other small things that are just a little bit too complicated to do directly in line with their separate functions. Let's see. I think I have some time left. So yeah, that's the runtime. And the runtime is also the... I've used a different... some people have suggested using the existing runtime for more compatibility. However, the goals of TinyGo are so different from normal Go that I decided to use a different runtime. Because, for example, the garbage collector is super simple, which is necessary because otherwise it's just too large. And for like 16K of RAM, you don't need an advanced garbage collector. And many other things are designed specifically for a small embedded system instead of large servers. However, all of my intention with this project is to be entirely compatible with the existing Go ecosystem, so that existing code can be reused on microcontrollers or WebAssembly, which is what many people are into, but I'm not really, to be honest. So some people have, for example, suggested stripping some parts from the language to make it smaller, but then you're breaking compatibility, and that's the whole point of the compiler, being compatible with existing code. Otherwise, you might as well just start a new language, write a new language. So, yeah, that's mainly my goal. I just want a compiler for existing code that's, but for a very different use case than it was used before. Thank you. Any questions?
So yes, we do have time for questions. So please, microphone in the middle, front.
Hi. Compliments on the idea of mapping.
Sorry?
Compliments on the idea of mapping an advanced language directly to binary code and making it very thin. Two questions or remarks, I don't know, about complexity. First is micro IP. I don't know if you've heard about it, but it used to be a TCP/IP stack that fitted in 16 kilobytes. And it was based on coroutines, so you might want to be interested in looking.
Sorry, I have
micro IP is a
IP.
It's a TCP/IP stack that fits in 16 kilobytes. It used to be run on microcontrollers, and it works through coroutines.
True?
Coroutines.
Coroutines.
So you might like looking into
in C or?
Yeah.
Interesting.
Yeah.
Maybe
I'll
useful for the
then we have to move on to the next.
Sure.
Please, just one question.
Okay.
But you can discuss
Might be useful for
afterwards.
the net package, which is not implemented yet, but thank you.
I was wondering, you spoke about the intention to support the full Go ecosystem. How do you plan to deal with like file system operations or other operations that would deal with an OS that is definitely not present in the embedded world?
So the file system, in Go we have the OS package, which is an abstraction layer over the operating system, of course. And what we've done in TinyGo is basically there's a function you can call to set a virtual file system at a basically to mount a file system at a certain path.
Okay, next
And
question.
that's how you can put in some file systems.
Okay, then
Thank
next
you.
question, please, front micro.
Hello. I was wondering, does the main issue with Go is it's too large to fit into microcontrollers, and therefore you wrote a new runtime,
Yes.
which is smaller so it can run on microcontrollers. But the language itself, you were just saying you wrote a Go compiler. Couldn't you just use the default compiler instead? Because what are the differences there? I was very curious about that.
So I've basically tried this. I tried to use GCC Go. GCC also has Go support. And my first attempt was using, and GCC also has a extensa port for the batch, for example. And basically what I tried was enabling the Go parts, and it did in fact work, surprisingly. However, I found that the way so the Go part was not very optimized. It uses all variables when you call a function, for example, all parameters are passed on the stack, and this wastes a lot of stack space. So it works on the ESP, which is pretty large, but on an AVR, it probably would be very difficult to get working. So I've looked into it, but the existing design was just not great.
Okay. And
Okay. Yeah.
are there any questions from the internet? No? Then next question, please.
A question about the garbage collection. Of course, garbage collection can get in the way of real-time performance, which may be a big problem for an embedded system. Have you taken care of that, for example, by trying to schedule it in downtime while it's waiting just before it goes to sleep, doing some garbage collection?
I've looked into it a lot, but right now it doesn't support this. However, what you can do is run the time-critical stuff in interrupts. And interrupts are not allowed to allocate memory. So this way, you can just do a garbage collection cycle while an interrupt is running. Basically, interrupt the cycle with an interrupt. So you can still write interrupt real-time codes and just not use heap allocation in there. So it's possible.
Okay, and one last really quick question.
Thank you. Sorry.
Front micro.
Work? Yeah, now it works again. I was also thinking about a system which was also meant for small processors, Java 2 Micro Edition, which run on the Nokias and so on. Could you use ideas from there? Because that was also a very small system with a garbage collector in case of Java.
Sorry, I didn't get that entirely. The question is whether
could you use ideas which were used in Java 2 Micro Edition, because it was also meant for very small systems, and it ran Java, which also needs garbage collection. So,
you mean compile Go to the Java bytecode?
Did you take it into? Did you take a? Maybe you could steal some ideas, so to speak.
I honestly didn't really look into it, but I know there are parts of JavaScript or Java are not.
Okay,
Java.
so that's something you can maybe discuss afterwards because time is up. And yeah.
If you have more questions, I'll be back here.
Yeah, and please give a warm round of applause because that was a great talk.